There we go. So chapter 8, all about Bode plots. And this is just one more tool that is commonly used in control systems. So you may have heard of Bode plots, or even in the lab, it may have shown up in different ways, maybe, maybe not. Again, this is along with things like root locus and root Hurwitz, just another tool of analysis that, yeah, depending on the application, can show up quite a bit and can be useful to know a little bit about it. So let's explore Bode plots. So let's start with, well, what are they? Okay. And so naturally, they're going to be graphs or plots. So I'll say they're, say graphs. And the main thing is that they're showing frequency on the horizontal. They're going to show magnitude and phase on the vertical. So I'll say they're graphs that show how the magnitude and frequency, I'm sorry, how the magnitude and phase. Okay, so graphs that show how the magnitude and the phase or angle, let's say, of the output of the system so how the magnitude and phase of the output of the system change or vary, let's say, as we increase the frequency of the input signal. So the idea, yeah, as we have input signals of different frequencies, does my turning up that frequency or turning down that frequency affect the magnitude and phase of the output? So oftentimes, just for keeping it nice and simple, we talk about amplifiers that for all frequencies, they just multiply everything by 10. And in practice, it's usually not quite like that. Usually as you're increasing that input frequency, there's going to be changes in the magnitude as well. So that's something to watch out for. Um, Now, what are they? And the next question that I'll ask here is, why should we care? Like, why are they useful? Why should we add these to our toolbox here with things we know how to do with control? So why should we care? Um, Main thing is they're a useful analysis tool. So they give us insight into certain things such as bandwidth. And we'll talk about bandwidth a little bit more in a sec. We have talked about bandwidth already in signals and systems last semester, but we will revisit that concept here in controls as well. And then also they give us insight into what's known as relative stability. Okay, relative stability. So this might seem a little bit weird in that we have talked about stability a lot in this class, and it's always, you're either stable or you're not, or you're right at the border. You could be marginally stable, but other than that, you're either stable or you're not. So it turns out it's not quite like that. So relative stability, this concept right here, it's all about, let's say, how close are we? How close is the system to instability. Okay, so we have so far we said, yeah, system is either BIBO stable or BIBO unstable, asymptotically stable, asymptotically unstable. It turns out that you can get more subtle than that and figure out, okay, yeah, we're stable, but are we actually pretty precariously stable? Where if we tweaked a couple of things, we would be over to the unstable side. So with Bode plots, you get a nice insight into that relative stability. How close are we to instability? All right. So next question might say, okay, so the Bode plot gives us this, gives us some insight into relative stability. So let's explore how does this happen? Let's say how to determine relative stability. Okay. So from a Bode plot. So in order to do that, I think it's easiest to just show you an example as to what that typically looks like. So Bode plots always come in pairs. I mentioned that there's a magnitude and phase of the output as we vary input frequency. So usually you're going to see a magnitude plot on top and a phase plot right below it. So there, yeah, that's going to be almost always what you're going to see. They're going to be in pairs. So let's draw one right here. And something like this. So this one, let's say we have a magnitude of G. And on my horizontal, I'm going to have my frequency. Let's do angular frequency, omega in radians per second. And then this magnitude, I'm actually going to take in decibels. So we'll talk about decibels in a little bit as well. Magnitude in decibels. So it's going to be a little bit different than just straight up magnitude. I'm going to do a little bit of a tweak. And again, maybe some of you have already seen decibels before, but if you haven't, we'll talk about it in a second. But again, like the idea being you can have a plot right here of magnitude as your frequency changes. So if something were a perfect amplifier, you would have something flat where gain doesn't change across all frequencies, but typically it does. For almost all systems, depending on the input frequency, you might have some changes. So let's draw a curve here. Let's say that here it's kind of nice and steady to begin, but then it begins to drop. And then let's say it does something like that. So yeah, maybe that's what your gain looks like right there. And right below it, let's draw a plot for the angle. So right below it, my horizontal axis is going to be actually pretty much the same. So I'll draw my horizontal. I'll draw omega in radians per second. And here I'm going to have my angle or phase in degrees. So let's say I've got 0 degrees, then let's make this minus 90. Let's make this minus 180. And let's say that this kind of drops. It starts at 0 like this, and then it begins to kind of go down a little bit. Maybe it kind of stabilizes here for a little bit, and then it keeps going down some more. Maybe it does something like that. So that's the way that you're going to get a phase shift depending on the input frequency. So as you can see, depending on that input frequency here, the phase shift is getting bigger and bigger. In this case, on the negative side, but there's more and more phase shift that happens as you increase that input frequency for this one. All right. So given a plot like this, let's see how we would determine relative stability from the Bode plot. Again, before we do that, before we determine the relative stability, again, let's just be aware of how to interpret these plots. The idea, you've got a frequency on my horizontal. So this is telling me, given an input frequency or an input signal with an input frequency, how does this modify the output? How does this modify the output? So here, if you had a low input frequency, well, you would get this big gain increase. But then if you increase that input frequency, gain would begin to drop. Here, we're actually dropping below 0 decibels, and we're going to talk about what that means. And then over here, we are there's going to be that angle that's introduced, this phase shift that's introduced. Okay. So the two main things that we're going to determine how say relatively stable a system is, it's through two things called gain margin and phase margin. So gain margin, write it up here. So it's going to be thanks to gain margin and phase margin. Okay. So let's start with this one, phase margin. In order to figure out phase margin, what we do is we check out where does the gain plot cross this 0 decibels line. So here we're going to mark this point. We're going to call that frequency omega C. And we're going to see for this one, how many degrees over 180 am I? So again, I take this omega C where I'm crossing over to the negative side. I mark it down here, omega C, and I check out what is my phase for omega C. If I'm above the negative 180, then I'm actually going to be on the stable side. What you want to make sure is that you've got enough of a buffer here. As you get closer and closer to the negative 180, your phase margin is going to drop. So phase margin is going to be that. It's going to be that difference in degrees between the negative 180 and whatever phase you've got at that. We'll write this down in a sec, but I think it's easier to show visually first. So again, it's how many degrees over negative 180 am I when this crosses over down to the 0. And just as a preview, usually you want to keep the phase margin at least at 30 degrees or more. Like if you've got 30, 40 degrees, you're in pretty good shape. But once it starts dropping to like 20 degrees, it means, yeah, the system's stable, but in terms of relative stability, it's not that stable. You're kind of in shaky ground at that point. The other one is gain margin. So gain margin, what you do is kind of similar. You actually come over to the phase plot first, and you see when am I crossing over to negative 180. And so for this one, it would be this point right here, which would correspond to this frequency. Let's call that one omega P. So omega P, again, is going to be the frequency when we cross over to negative 180. Then I would come over to my gain plot and mark omega P. And I would check out how many decibels, how many decibels below the 0 am I? How many decibels below the 0 am I? And so this right here would be your gain margin. And here you're hoping for a little bit of a buffer, just like you needed a bit of a buffer here. So usually if there's at least 3 decibels difference you are in good shape. Like 3 to 6 decibels would be great. Anything more than that is also good. But if you're a little close of just having like 1 decibel difference right here, if this were like up here pretty tight, that might say, okay, the system's stable, but it's pretty close to instability. So that's the two big tools right there, gain margin and phase margin. And so you could take any MATLAB generated Bode plot, which MATLAB is quite good at generating Bode plots, giving you pretty detailed plots, and from there figure out gain margin and phase margin pretty easily. So that's how visually you would pick it out. And again, it carries with it quite a bit of information about relative stability of your system. Okay. So just to sum that up in terms of phase margin and gain margin. So phase margin, so we all have it. Okay. It's how many degrees? How many degrees, let's say above negative 180? Is our phase. At omega c. And again, omega c is the frequency at which the gain equals 0 decibels. It's actually, this omega c is known as a crossover frequency. That's the special name, crossover frequency. And then I'll say for a robust system, let's say we want gain margin or phase margin rather. Let's say of at least 30 degrees. You get a little bit more, great, but at least 30 degrees would be good. And again, gain margin. It's kind of a symmetrical sort of definition. So you ask yourself, how many decibels below 0? Yeah, how many decibels below 0 dB is our gain. At omega p. With that omega p is going to be the frequency at which our phase is negative 180. And again, for a robust system, we want a gain margin, say of at least 6 decibels. I think that would be nice and solid. So notice with this, again, you can be given any MATLAB generated plot, figure out that relative stability pretty easily just with visually looking at it. I'll add that there's some control designers that they build their whole thing, just as we've had things like, oh, put your poles in this location. There's going to be situations where you're putting, rather than have specs like that, someone might ask you, hey, could you make sure to design a controller so that the gain margin is so much or the phase margin is so much. That's going to be another thing that we do. So I'll say sometimes.
Dr. Expada.
Yes.
Is there like also another name for WP like there is for the crossover frequency?
Yeah, good frequency. Good question there on the frequency, because that's the one thing that's like not symmetrical, but it doesn't have a special name, which is unfortunate. In some textbooks, they don't even give it like I denoted by a special letter. Even they just will tell you just observe where it hits negative 180. But yeah, so it doesn't really have like a special name to it. But that's a good question, Quinn.
Okay.
So yeah, so we'll just keep calling it omega p here. But yeah, and so just to wrap up here, it's like sometimes let's say GM, yeah, sometimes control designers use the GM and PM as specs to build the controller. Okay. All right, so something I've mentioned a couple of times is this concept of decibels. And just to check for you guys in here, have y'all seen that before? Decibels, or Eva saying yes, Hunter saying yes, Home is as well. Um, can you just type into the chat box if you have not seen decibels before? Because I mean, these guys are mostly on the EE side, so maybe it hasn't come up for those of you that are in other concentrations. All right, so I'm not seeing anything, so I'll just we won't do a whole lot of practice with decibels, but I'll just give you the definition or just a quick reminder in case you have forgotten. So typically the most common definition of, for example, here, a gain in decibels, it's going to be 20 times log base 10 of, let's say, magnitude of output divided over magnitude of input. Okay, so that's your typical thing. Now, sometimes you might, when you're talking about power, rather than other quantities such as voltage or intensity. So if you're talking about power, you might see this with a 10 rather than with a 20. For us in this application, we're going to use 20 out in front. So 20 log base 10 of this. So just a super quick example. So y'all are not scared away by it. So let's say if, yeah, like if x of t was, let's say, let's do this. Let's say x of t was 10 cosine of 3000 t. And that's my input. Okay, so that's my input signal right there. And y of t, my output. Let's say that it's 1000 cosine of 3000 t. I'll ask what is the gain in dBs? At 3,000 radians per second. So what's your gain right there? Just in decibels. So hopefully you're doing that pretty quick there at home or wherever you're at, and feel free if you're here to shout it out. Otherwise, you can type into the chat box what you got as your answer. Simple plugging in into that formula, right? But okay. So Quinn tells me 40 decibels indeed. Great. So notice that we are dividing the magnitude here of the output divided by, or divided over magnitude of input. So 1,000 over 10 is 100. 100, then we take log base 10 of 100, that is 2, because 10 to the 2 is 100. So indeed, we 20 times 2, which is 40. Yep. So good work. So that's going to be 40 decibels. So let's repeat. Let's say we have the same, say x of t is the same thing of 10 cosine of 3,000 t, and then y of t is, let's say it's just 1 cosine of 3,000 t. So what is the gain in dBs here? And I'll do one more. Let's say, again, same input, x equal 10 cosine of 3,000 t. And y of t is, let's say it was unchanged. You got it the exact same 10 times cosine of 3,000 t. Okay, just so we get a little bit more intuition as to what these decibels imply. So please type into the chat there your answer for B. So I got quite a few people there that are all chiming in with -20, and that is of course correct. -20 decibels. That's right. So notice that something that's different from linear gain is that we are seeing a negative, even though we're not changing sign, right? We're not changing sign. What we did was get smaller. So whenever you see negative decibels, it does not mean inversion. The inversion is going to show up in the angle. If you see an angle of -180, that's going to be inversion. But for us, when you see negative decibels, just means we got smaller here in terms of the output being smaller than the input. So -20 right there. And then, well, hopefully you can see, or you might even guess, if negative is when we get smaller, positive is when we get bigger. If you stay exactly the same, that's going to be your 0 dB case. So all those things about when we hit 0 dB, that is when my output and my input are of the same magnitude. Okay. Now, this is often used, yeah, in a lot of controls, communications, especially when you've got big variations in terms of the magnitudes of input and output, because the decibels make it a lot more manageable. So for example, this one, let's say we had, let's say instead of having 1,000, if over here we'd had, I don't know, 100,000. 100,000. So between 10 and 100,000, that's a huge difference. And so you're already manipulating massive numbers in terms of gain. But then when it comes to decibels, you're like you divide, and then thanks to the log 10, you're going to get numbers that are a lot more manageable. So for this one, it'd be let's say 100,000 over 10. That's 10,000. Um, and then 10,000, that is what 10 to the 5, right? So the 100 decibels for that one. Okay. So that gives you an idea of how decibels are used, and that's going to be the main thing that we see there on the vertical of the graph. So again, if, just I guess a little refresher if you've seen them before, but you haven't seen them in a while. So all this talk of like how many decibels, this is where it comes from. All right, so now we know about decibels. We know how to interpret these Bode plots that gain phase margins. So we're doing pretty well. Now, some of you might be wondering, okay, that's good, but how do we sketch this? Like, how do we, given a transfer function, how could we draw a Bode plot? So let's yeah, let's explore that a little bit. So I'll say how to sketch. A Bode plot. And usually given the transfer function of the system. So someone told you, hey, this is your system right here. It's got transfer function G of S or H of S or whatever. So how do you sketch a Bode plot based off of that? Now, the absolute easiest way is to use MATLAB. So you give it, you just use a command called Bode, and Bode, and in parentheses, you put your transfer function. Actually, I think the syntax is Bode numerator comma denominator, but that'll spit out a beautiful Bode plot. However, if you want to, kind of like we did with root locus, so it's a similar thing. In MATLAB, your root locus, you can get it by typing R locus of your system. But it's helpful to know just some of the basics of how to sketch a quick one by hand. So we're going to do something similar of just getting a rough idea of how to do it by hand, just at least with basic steps for so that we know where these plots come from and that it's not some magical thing. So how to sketch Bode plots given the transfer function of the system. Let's say you've got, let's say it's transfer function, let's call it G of S. G of S. All right, so first thing we're going to do, so how to sketch it. So first, we're going to factor both the numerator and denominator. And we're going to do it in the following way. So get it so that you've got G of S. You're going to take, let's say this form, let's call it K0. And then the numerator, usually you have a polynomial, but factor that out. So you've got S plus, let's call it omega 1. S plus omega 2, and so on. So basically, the numerator, you're factoring out an S plus this, S plus that. and so on. So if you had like an order 3 numerator, you would have 3 of these terms like this. You would put any gain here out in front, and you would do the same here for the denominator. So usually, you'd have like s to the 5 or s to the 4, whatever. Here, you're going to factor it out. And so let's call it s plus, let's say omega 3, s plus omega 4, etc. Okay, so just make sure that you're factoring out the top and bottom. Then next thing we're going to do is that s turn it into a j omega. S becomes j omega. Okay, so now you've got,
Can't we so for the top part where you're just talking about with the K, that's the same as the ZPK form.
Yeah, that's right. So with MATLAB, you can use ZPK. That's right.
Okay.
Great. Yeah.
So if we had like a function in a different form, we could just use the I think it's TF to ZPK.
Yes. Yes. Absolutely. Absolutely. That
Okay.
would be the most. If you got MATLAB with you, that's the most efficient way to do it. Indeed, TF to ZPK, and that would set it up this way for you. Yep. Exactly right. So indeed, so now, yeah, just wherever you have an S, you turn it into j omega. So this would be k0, then j omega plus omega 1, j omega plus omega 2, here at the bottom, j omega plus omega 3, then j omega plus omega 4, and so on. All right. Next to each of these terms, we're going to factor them or modify it in the following way. So you've got at this point j omega plus omega 1. We're going to divide this term by omega 1 so that you get 1 plus j omega over omega 1. So I'll say next, we're going to do this step. So our g of j omega. So this term right here, where we had j omega plus omega 1, we're going to write it this way, j omega over omega 1 plus 1. Okay, so we divided both terms by omega 1 so as to get 1 plus j omega over omega 1. And same for this one, we're going to divide by omega 2. So you get j omega over omega 2 plus 1. And same for these guys here in the bottom, j omega over omega 3 plus 1, j omega over omega 4 plus 1, and so on. So we are factoring top and bottom. So you got 1 plus j omega over these various frequencies. Now, you might say, wait a minute. So here I divided by omega 1, I divided by omega 2, down here by omega 3 and omega 4. So all of that dividing that you did is going to get absorbed in your constant. So all this, instead of having k0, let's just have a k. K basically absorbs any constants you divided by or multiply by. All right. So at this point now, we've got essentially 3 types of terms. We've got the gain k. We've got these zeros, basically. These are zeros that are factored out in this fashion. And then you got poles. And so what we're going to do is basically next, take each factor separately. Take each factor separately. And then and I'll show you in a sec what each factor does. And then finally, combine, say, the effect of each factor. Into one plot. So again, you could have a number of these at the bottom. You're going to have a gain K out in front. So we're going to determine what each of these things is doing, and then we're going to just kind of superimpose all the graphs together, and that'll give us our overall Bode plot. All right, so let's investigate what each of these factors does. So let's ask, what does each factor do? All right, so the first type that we had was our good old plain old gain. So here we had, let's say that we just have a gain. So G of J omega is just equal to K. So if all you have is K, I'll draw over here. Our plots. So again, they always come in pairs, always one right above the other. And so I'm going to have my horizontal omega. Then this one is magnitude of G and dV. This is going to be angle of G in degrees. So the gain is pretty straightforward because it's going to be nice and flat across all frequencies. Nice and flat across all frequencies. So if all you have is a gain, it's going to be true for all frequencies. And here, notice it's not going to be just K, it's actually going to be, because of the decibels, 20 log of K. 20 log. Okay, so that's contributing. It contributes nothing at all in the angle. So that's going to add 0 degrees, and those 0 degrees are going to hold all the way. Okay, so pretty, I think, intuitive and straightforward there, that a gain would just bump up your gain. So it's kind of whatever else you had is going to bump it up by this amount, and then the phase stays the same. Okay. So that's our first type of element. The next one was 0. So the second type, so this first one was a gain. The second one's going to be a 0. So what if your transfer function is just of the form G of J omega equals, so you only have something in the numerator, so 1 plus J omega over omega 1. Okay. So normally here you'd have a gain and you'd have stuff in the denominator, but let's say that we only have that 0, only that in my numerator. So let's check out the effect of that. So I got my two plots there in the top and bottom. So the first one is going to be this magnitude of G. This one's going to be angle of G. Of course, this is in decibels. And this is omega and omega in radians per second. Now, for this one, what's going to happen with a 0 is that you're going to be nice and flat at 0 decibels up until you hit this omega 1, up until you hit that omega 1. So at omega 1, then your 0 is going to give you a steady increase right here. A steady increase of this slope, the slope of this incline is going to be 20 decibels per decade. 20 decibels per decade. So a decade means when there's a factor of 10. So let's say that here, let's say this is plus 20 decibels. So this is gain in dB. So this would be plus 20. So this here would correspond to 10 times omega 1. Okay, so basically that when you multiply by 10 in my horizontal, that's going to give you plus 20. Now, something that's interesting about these log scales, and some of you might remember, is that this distance right here. So if this was 10 omega 1, if I do the same distance on this side, this is going to be the other power 10. So over here, you'd have like 0.1 omega 1. If you were to continue this for the same distance right here, you would have 100 omega 1, and that's where you would hit the 40 and so on. So they're definitely very different from a linear scale in that regard. All right, so that's what R0 is doing. Then what else? Here on the phase, what we do is we mark these three, the omega 1, the 0.1 omega 1, and 10 omega 1. So mark those three. And basically what's going to happen is that the 0 is going to contribute 90 degrees of phase, plus 90 degrees. But they're going to happen eventually. We're going to hit that that negative or that positive 90 eventually. And by eventually, I mean basically when we're at the 10 omega 1. We're going to be at about 45 degrees. We're going to be at about 45 degrees at omega 1. And things are going to start to kick in at 0.1. So it's going to look a little bit like this, where you've got it nice and flat. It's not affecting it until you get to 0.1 omega 1. And then this thing starts to pick up a little bit here. It starts to pick up. And then it keeps going up, and it'll flatten out. It'll flatten out at plus 90. And maybe there, I drew it a little bit too linear looking. It's actually a little bit more curvy than that. So a little bit more like this, where it starts like that, kind of goes up, and then flattens out. So that's what your 0 is going to do. Again, plus 20 dB per decade here, and this steady, eventually a plus 90 that starts to kick in at 0.1. All right. You might guess a pole is going to do mostly the opposite of that, and indeed that's the case. But let's write it out explicitly. So a pole, that's if you had G of J omega equal 1 over, and we'll put J omega over 1. So again, you might have a K or other stuff around, but if you only had this, we're going to consider that individually. So this is what is going to happen to us in terms of gain and angle. So I'll actually leave a little bit of space downward here. This is going to be gain in dB. This is going to be omega. And then over here, I'm going to have my angle of G. Again, versus omega in radians per second. All right. So it's going to be really similar to what we had before. So let's mark the omega 1. I'll also mark the 10 omega 1 and the 0.1 omega 1. So on the gain side, we're going to have nothing, nothing, nothing until omega 1, and then it's going to kick on. And then it's going to kick on at about minus 20 dB per decade. So something like this. Okay, so this is right here. This would be minus 20. So slope is minus 20 dB per decade. All right, so similar idea just on the other side. And also here, just as the other one contributed plus 90, this is going to give me minus 90. But it's going to kick in here at 0.1, and it's going to finish kicking in at 10 omega 1. So let's mark those 10 omega 1, omega 1, 0.1 omega 1. So it's really doing kind of nothing here. Then it's going to start to kick in at this point, and then it kind of levels out there. It levels out like that. At negative 90. Now there's so now we've done gain, zero, and pull. And you might say, well, we're done. That's the three types that we got. We're actually going to do two more, a variant on the zero and a variant of pull. So what happens if rather than have the 1 plus j omega over omega, what happens if it's right at the origin? If we just have a j omega at the bottom, just plain and simple, which would correspond to just having an s there. So that's going to be just slightly different. So let's do number 4. Let's say, let's rather than point, let's do 0 at the origin, since we did it in that order. So if we just have g of j omega equals j omega. So let's go ahead and plot this one. Okay. So that's our plot for magnitude, and right below our plot for angle. Okay. So when you have this situation of a 0 at the origin, so we know that a 0 of the origin is going to give me that positive slope of 20 dB per decade, but it's going to kick in at omega 1. And here we're not really talking to omega 1 at all. Here it would give me that minus 90 or plus 90, but it would kick in at omega 1 or at 0.1 omega 1. And here we don't have an omega 1 at all. So when you have this, basically this pole or this 0 in this case has been on all the time. And so my gain is going to be up at plus 90 the whole time. Plus 90 the whole time. And then up here, that what it does of like kicking in, it's actually going to give you the plus 20 dB per decade. Again, let's say quote unquote the whole time. So you're going to have plus 20 dB per decade. And so you might be wondering, wait a minute now. So if this slope is going the whole time, like where does this crossing happen? Like that might be your first question. I mean, we don't have an omega 1 or anything. So basically you're going to hit the value of this crossover right here is going to happen at omega equal 1. At omega equal 1. All right. So a bit of a conceptual question here, but notice I've got this it's kind of a sloped line right here. So what would be like, am I not going to hit this axis? Like at what point would I cross this vertical axis right here? Like, is there a y-intercept, sort of, so to speak, right there? What do you guys think? Like, if I'm dropping here 20 dB per decade? Paulo, I see you typing.
You'll get closer and closer to, uh, yeah,
So as I'm getting closer and closer, right, I'm getting, this is dropping further and further, which is a little bit weird. And we're saying the graph doesn't exist past this point. This is true. This is true. The graph doesn't exist past, we're not defining it on this side. And in fact, we're not defining it right at the zero. We're taking this, let's say this point as a reference, and then we're adding 20 dB per decade. So this is 20, this is 10 omega 1, and so on, and this would be 0.1 omega 1. If we wanted to look here to the left, we would have to expand the graph to the left, because every time that we divide by 10, we're adding a block of the same size. So again, that's one of the tricks of this log scale on your horizontal. So really, you've got a little break right here. You've got a little break right there. It's not quite just what we're seeing there. And if you wanted to draw a little bit more, you would have to draw more things. So you're actually never quite getting there in terms of in this log scale right there. So just be mindful of that. Great. So that's going to be our 0 at the origin, and then finally, as you might guess, just as we did 0 and pole, they're going to be a pole at the origin, which is going to do essentially the opposite of what this one does. So the last term is going to be number 5, pole at the origin. So G of j omega equal 1 over j omega. All right, so if you have that, so this is kind of like having a 1 over s there. So let's draw our pair of plots. We're going to have omega here in the horizontal, G in decibels here. We're going to have the phase here on the vertical and omega on the horizontal. Great. So it's going to be essentially the opposite. Just as the 0 added 90 all the way, this is going to subtract 90 all the way. So it's going to be minus 90 degrees the whole way. And just as this one had that, we had that positive slope of 20 dB per decade, that's going to have a negative slope right there. So here it's going to be minus 20 decibels per decade, centered again at 1. So this here, for example, was 20. This means that we're at 0.1 omega 1, or yeah, 0.1 simply. In fact, going back to this one, I'll correct this one from number 4. Here I called it 0.1 omega 1 and 10 omega 1. So there's actually no omega 1. Here it would just be 0.1 and 10. Sorry about that. 0.1 and 10. So same here, you got 0.1, 1, and 10. Right. Now, one that we're not going to get into here just to save a little bit of time, but notice that everything that we've done as far as factoring terms implies real numbers. So for example, here, going back to this sheet, we've got a pool of 1 plus j omega over omega 1. So you may wonder, well, what if there's complex roots? So if there's complex roots, you would actually keep it as a quadratic term rather than factor out those. And there's a way to explore what happens with the quadratic term. Just, for the sake of simplicity, I'm not going to go into that here. We'll just explore these 5. But there's essentially a quadratic term is going to drop you a straight minus 40, like rather than do minus 20, it's going to be minus 40 dB per decade. There's a couple of other things to consider, but honestly, when you've got a quadratic term and other things, you can always just resort to MATLAB. So this is just a quick sort of back of the envelope sort of thing to get an initial idea of what it's all going to look like. All right, so at this point, we have broken down our transfer function into its components. We have identified what each component does. And you know what? Let's leave it right here. And then on Thursday, we'll do some practice as to how to combine them and do different things with them. All right, so thanks for your attention, folks. And I shall see you soon.